Hi, Algebra 2 friends. Here we are in Chapter 12. We're looking at Section 12.4. We're going to be multiplying probabilities. The only vocabulary phrase we have today is area diagram. And what we're going to talk about is how we can look at probability of two independent things and an area diagram that will relate the two. For instance, let's say there was a, 80% chance of rain. All right, so that's a 0.8 probability of it raining, and therefore the probability of it not raining would be here at 0.2. And let's say there was, 6 out of 10 chance that I would have access to our family car because I share it with my husband. There's like a 40% chance he might be called into work. So what we have here is a diagram that's going to help us kind of represent what are our what are the possibilities that could happen, or really the probability of the different possibilities that could happen. So let's watch. So now what I'll do is I'll multiply each of these to figure out what that area would be, but it also gives me the probability of the two events occurring at the same time. So when I multiply 0.8 times 0.6, I'm going to get 0.48. When I multiply these guys together, I'm going to get 0.12. Over here, I'll get 0.32, and over here, I'll get 0.08. So this type of an area diagram is a handy way to determine probabilities in situations like this where you have variables that are independent, but you can combine them to figure out the probability. So clearly it's pretty likely, the most likely thing that could happen would be that it rains and I get the car. But it's also kind of likely that it could rain and I don't get the car, or, I could get the car and there's no rain, and you guys get it. Very unlikely that I won't get the car and there won't be rain. All right. So one of the key concepts that maybe you saw or witnessed in that diagram, or, that will make sense to you, especially given like the fundamental counting principle, it kind of relates in a way, is that if you have two events that are independent, then the probability of both events occurring, that is the probability of A and B occurring, is whatever the probability of A is times the probability of B. In example 1, we have two independent events. At a picnic, Julio reaches into an ice-filled cooler containing 8 regular soft drinks and 5 diet soft drinks. He removes a can, then decides he's not really thirsty and puts it back. What is the probability that Julio and the next person to reach into the cooler both randomly selected a regular soft drink? So we've got Julio, who was choosing out of the 13 total number of cans of soda. He was able to pull out one. We want to know what was the probability that that particular one that he pulled out and then returned was a regular soft drink. Well, that would be 8 out of 13. That's the probability of Julio pulling out a regular soft drink. All right, so I'll just call that probability of R dot S. And then so he returns it. So what we realize is the choice of the next person who comes in is not different than Julio's choice. And so that person has a choice out of 13, 8, to pull one of 8 out of 13. So the answer to the question, so the probability of this circumstance, let's call it an A and B, where Julio picks a regular soft drink and the next person picks a regular soft drink, would be the product of 8 over 13 times 8 over 13, which is going to be 64 out of 169. That's our probability. So this type of thinking even works when we have 3 independent events. So here in example 2, in a board game, 3 dice are rolled to determine the number of moves for the player. What is the probability that the first dice will show, or the first die will show 6, the second die will show 6, and the third die does not? Okay, so we need to think about these different events. So even though it's not stated, we're talking about a six-sided die. And so even if we are choosing what's the probability of the first one being six, well, that's going to be 1 out of 6, right? The second one would also be 1 out of 6 for that particular die. Now for the third one to not be six, it's got 5 out of 6 choices. So what's the probability? Well, it'll be 5 out of 216 when I multiply all the sixes together into 1 times 5. That's what we get. Now, this next concept is what we need to think about when we are dealing with dependent events. If two elements A and B are dependent, then the probability of both events occurring, that is the probability of A and B in this situation, is that it will be the probability of A followed by the probability of B following A. So that seems like a little bit of gobbledygook. But if I were to have like a bowl containing 3 apples and 2 oranges, and I were to consider the probability of choosing an apple and an orange at random, of course, just I don't know, dumping out a fruit and seeing which one will come out. And what we would do is we would say, well, the probability of getting an apple would be 3 out of 5, right? But the probability of getting an orange, now that one apple is gone, would be 2 out of 4. So the combined probability of me grabbing an apple and an orange would be this, 6 out of 20, or 3 out of 10. I don't know about you, but I was also thinking, well, what would happen if we did it the opposite way? If we pulled an orange first and then an apple. And so our situation would be, well, there's 2 oranges out of 5, but then if we've done that, there's one less thing to pull from, and therefore there's 3 apples out of 4. And if you notice, 3 and 2 are in the numerator, 5 and 4 in the denominator. We get the same probability. In example 3, we're looking at the host of a game show is drawing a chip from a bag to determine the prize for which the contestants will play. Of the 10 chips in the bag, 6 show television, and 3 show vacation, and 1 shows a car. If the host draws the chip at random and does not replace them, find the probability of a vacation and a car. Well, since there's 10 chips, the probability of a vacation would be 3 out of 10. The probability of the car would be 1 out of 9. Therefore, we're looking at 3 out of 90, or 1 out of 10 would be the probability of the vacation in a car. 2 televisions would be 6 out of 10 because there's six that show the word television. And then if we take 1 out, then there would be only 9 that are left, 9 chips in all, and there would only be 5 of the 6 television chips left, and therefore we would get 30 out of 90, which reduces to 1/3. In example 4, we're going to look at 3 dependent events. 3 cards are drawn from a standard deck of cards without replacement. Find the probability of drawing a diamond, a club, and another diamond in that order. Knowing that a standard deck of cards has 52 cards and 4 suits, that means that 1/4 of the 52 cards, or 13 of the 52 cards, will have a diamond. So the first pull of a card would be 13 out of 52, or 1/4 of a chance that we have a diamond. And now we can consider each of the other ones. I had this wrong here. So a club, there's 13 clubs, but now we only have 51 different cards left. And so that's for the club situation. And then finally for the diamond, the final diamond, we've already chosen 1 diamond, so we only have 12 left. And then that would be out of 50. So when we multiply the numerator by the denominator, well, the numerators together and then the denominators together, this is what we get, 850 rather. And so we can say that this is the probability. Of course, in all of our examples, we can use probability in terms of the decimal form. So we could write the decimal form of this answer, which is about 0.015. And we could have done that for some of the other ones as well. All right. With that in mind, guys, I hope that you are doing well. I hope this makes sense. And I look forward to talking to you soon. Take care.